Let's discuss bonding in coordination compounds. The theories to describe the type of bonding in coordination complexes is given by Alfred Werner, by his Werner's theory of complexes, or by VBT and CFT crystal field theory. So let's consider Werner's theory of complexes, where he suggests any coordination complex exhibit two types of valencies, primary and secondary valencies. A primary valency is actually ionizable valency, whereas a secondary is non-ionizable. So basically, let's consider the example K4FeCN 6 times. Let's identify which is the primary and secondary valencies. Primary valency is basically the oxidation state of metal atom which is present in the coordination sphere, whereas a secondary valency is the coordination number. What is the coordination number? The total number of ligands surrounding the central metal atom in the coordination sphere, or it is the total number of sigma bonds present in the coordination complexes. So primary valency is ionizable valency because from the oxidation state of the metal, you are getting some charge on the coordination sphere, and which is actually balanced by the presence of either a cation or an anion. So that is ionizable. For example, if you consider this system, it ionizes to give you 4K plus FeCN 6 times, 4 minus. So ionization is possible here, but when you consider the number 6, which is the coordination number, is not ionizable, and that is the secondary valency. So whenever you consider the coordination number for a particular metal atoms or metal ions, their coordination numbers are fixed. For example, if you consider Fe2 plus or Fe3 plus, their coordination number is fixed as a 6. Whereas if you consider platinum, they can exhibit a coordination number either 6 or 4. So for a particular elements in their particular oxidation state, their coordination numbers are fixed. The Werners theory is actually proved by knowing the electrical conductivity or by the precipitation technique. If you consider an example, Fe NH3 6 times Cl3, let's add AgNO3 so that you are getting 3 moles of AgCl. So presence of 3 moles of AgCl precipitation indicates 3 chloride ions are actually present in the ionization sphere. They are existing in the free form, they are not in the combined state and present in the coordination sphere. So this indicate they have 2 types of valencies. One is called primary and the other is called secondary. If you consider the electrical conductivity, let us consider the example of platinum complexes, Pt NH3 6 times Cl3, Pt NH3 5 times Cl2, Pt NH3 4 times Cl2, Cl, and Pt NH3 3 times Cl3. So these are the coordination complexes formed by the platinum when they are reacted with ammonia and chlorine. When you consider the first example, prepare the solution of this complex so that now it exists in the form of Pt NH3 6 times 3 plus and you have 3 Cl minus. Indicates it results in a total of 4 moles in the system, therefore the conductivity will be corresponding to the 4 moles. But if you consider the second example, Pt NH3 5 times Cl2, it decomposes to give Pt NH3 5 times Cl 2 minus plus 2 Cl minus, where now the total number of mole is reduced to 3. Consider this third and fourth example, which gives you Pt NH3 4 times Cl2 minus and Cl minus, whereas in the final stage you have only 1 mole because further ionization is not possible. So the existence of an ionization sphere and coordination sphere is actually proved by knowing the electrical conductivity of such complexes. So whenever you have more number of moles present in the ionization sphere, you are getting more conductivity for that solution. So this is how Werner explained the two types of valency, primary and secondary valency. He also suggested that when most of the coordination compounds have a coordination number, either it can be 2, 4, 6 or 8. 8 is the coordination number exhibited by molybdenum complexes and 2 is by silver gold complexes. Usually most of the coordination compounds are with the coordination numbers 4 and 6. He also suggested the structure of such compounds. If you have the coordination number 4, then the structure can be either square planar or it can be tetrahedral. If you have coordination number 6, it can have only octahedral geometry. So Werner suggested the types of valencies and the possible structures for the given coordination numbers and their electrical conductivity.